Anybody got any questions or anything we need to discuss before we get started? Good deal. All right, you guys may remember last Monday, so a week ago when we were our last meeting, we looked at logic gates. We started talking about digital, and we're going to kind of back up just a little bit so I can connect some of what we went over at the end of last Monday to some of our number conversions that we're going to go through. So we won't spend quite as much time going through this presentation in terms of logic gates, but just to kind of a refresher to make sure that we're all still on the same page in terms of these digital logic gates. Did the screen change for you guys?
Yeah.
Good deal. All right. I just really want to get to kind of a refresher of the different gates that we have. Remember, we were talking about a variety of different gates, and we threw a bunch at you right at the end of the session. Remember, we're talking about building these truth tables where A is our input, F is our output. Typically we're going to have at least two inputs, except for these first two gates, and then we can't have more, right? And we can build these inputs based on whether we have a 0 or a 1, 0 being a low, 1 being a high, and build these circuits so that we can get an output for a given input, right? So we can, in essence, have something happen at the end of this circuit based on these inputs, if they're in the right position, or if the logic is right. Okay, so the buffer, we said the A was equal to F. That was the Boolean expression. That's our mathematical expression where we're going to write basically what's happening in our truth table. Basically this buffer was nothing more than an opportunity for whatever comes in is going to be the same that goes out, right? And we'll see once we start. Well, I was going to say I'm not sure if we'll actually get into a circuit that will have a buffer or not, but there could be some reasons to use a buffer. But A is going to equal F, right? The input is going to equal the output. The output's going to equal the input. The NOT gate, two different ways of writing this gate. You can see we've got this bubble inverter, this little circle on the output. And all that means is whatever the output would have been, we're going to change it. And so this is going to be read A is equal to Y naught, right? And so meaning that whatever A is, and remember, since we're talking about binary, we're talking about digital, we're talking about only two states, either 0 or 1, low or high. Whatever A is, F is going to be the opposite, right? You can look at our truth table and see that if A is 0, F is 1. If A is 1, F is 0, right? And so A is equal to F naught or Y naught, as we're saying it here. The only difference in the way you can interpret, the way I like to think about these two drawings in terms of this NOT gate, this, I think of it as a typical buffer with an inverter on the end, meaning that whatever it typically would be, I'm going to invert it when it gets to this this bubble inverter, and it's going to become the opposite. Typically for a buffer, if A was 1, F would be 1. Well, as that 1 comes through this buffer and gets to this NOT portion of the gate, it's going to be inverted. And so if A is 1, it comes out as 0. The other way to represent this same NOT gate, you're going to get the same thing. Basically, if A is 1, it's going to be inverted as it goes in, and it comes out as a 0. I like to think about this as a state indicator. You hear it referred to as a state indicator. And so this indicates that this input is active low. And this will make a little bit more sense once we get to some other gates and we start looking at trying to make sense of what's happening. Why it's easier to think about this being active low, the state indicator. All right, so it's going to be active low, meaning that I'm going to get a high out when I get a low input. Well, I get a 0, I'm getting 1 out. Still holds true. I mean, the truth table is still the same for either way you think about this NOT gate. But we'll see once we get into what we're going to call flip-flops. We'll see the state indicator and this notion of a state indicator, and that kind of thought process will play out. It'll be more advantageous to think about it in those terms. Either way, though, we're going to get the opposite out of what we put in, and that's a NOT gate. Right? We're going to fly right through these quizzes since we did them on last Monday, and we're just going to hit the different gates. The AND gate looks like the letter D, right? We've got 2 inputs, an A and a B. And what we said, the Boolean expression A and B equals F, right? A and B equals F. And what that means is that in order for me to get a 1 out, a high out, a true out, I'm going to have a 1 on A and B. And meaning both, right? And so you can see that truth table, that's the only time I'm going to get a 1 out is when I've got a high on or a 1 on A and B, then I get a 1 out. All the other instances, I'm getting a 0 out. It doesn't satisfy this Boolean expression, A and B. All the others, I could have one or the other or neither. Doesn't matter. I'm going to get a low or a 0 out. If you guys have any questions, just stop me as we're going through these. I just wanted to refresh. OR gate. Notice the difference. Notice how it looks different, right? This OR gate, the Boolean expression, A or B equals F. Basically, that means that if I get a high on A or B, either one, I'm going to get a high out. A 1 on A or B, I'm going to get a 1 out, right? And so if we look at our truth table, we see how that holds true. I had a 1 on B, I get a 1 out. I had a 1 on A, I get a 1 out. I had a 1 on A and B. There's nothing that says for this gate that we can't have a 1 out. And so if I get a 1 on either input or both, I'm getting a 1 out. You can see how that truth table looks different than an AND gate.
Shouldn't that be 8 times B? I'm getting confused here. So you got 1 plus 1.
So is your question about
The expression? How you have A plus B equals F?
Yeah. And so really this plus, it's not so much a plus. And when we're talking about Boolean, what it is, that is actually saying or, right? So this is recognized as or.
Okay,
right?
I got it.
A 1 on either one of these, A or B equals F, right? When we had the multiplication in the last expression, we're going to use that multiplication symbol as and, right? So A and B, meaning both of them, would be F. Here it's or, A or B. And so we're really we're not applying mathematical, we're not adding these together, right? To get
I forgot. We're working with 1s and 0s.
Exactly.
I forgot.
Exactly.
Yeah, I got it now.
Good deal. Good question, though. Now, exclusive or, we had a couple gates that take it to that next step. Exclusive or, what that says is that here we are with a plus with a circle around it, right? And so we're going back to that OR gate. So this is A or B, but not both, equals F, right? And so what it's meaning there is that if I get a high or a 1 on A or B, but not both, if I get a 1 on both of these, then I want my output to be low. And so we have here, if we look at our truth table, anytime I have a high, I'm going to get a high out, right? And so B was high, I get a high out on F. A was high, I get a high out. But when both are high, then I get a low out. I get a 0, right? And so this was a gate where I want either or input high, I get a high out. But if both are high, then I'm going to get a low out. So this is our exclusive OR, or XOR. We had a NAND gate. Our NAND gate, now we're just basically putting that bubble inverter on the output. Still an AND gate. It's just that our truth table is going to be completely inverted, because what I would expect out is going to be inverted, and now I get the opposite, right? And so before, when we had an AND gate, the only time I would get a 1 out is if I had 1 on A and B, right? Had to have both inputs high to get a 1 out, to get a high out. Here, if I had both inputs high, I would expect a high out, but it's going to be inverted for a NAND gate, and so I'm going to get a low out. And so the table, the truth table, is just going to be completely inverted. So before, for an AND gate, we had an output of 0, 0, 0, 1. Now we've got an output of 1, 1, 1, 0. It's just completely the opposite. We can see how those two tables look when they're side by side, right? 0, 0, 0, 1 for my outputs, and then I get 1, 1, 1, 0. So that was the NAND gate. If you feel comfortable with the AND gate and the OR gate, usually you can create the truth tables for the others with very little problem. You hear the NOR gate. Once again, it's the OR gate, except for I've got this bubble inverter on the output, and so it's going to be just the opposite of my typical output. Remember, for an OR gate, either input being high would give me a high output. 1 on A or a 1 on B would typically give me a high output for an OR gate, but I'm going to invert it. So anytime I get a 1, now I'm going to get a 0 out, right? And so if you look at our truth table, anytime I get a 1 on B, 0, a 1 on A, 0. Now this is just a NOR gate, and so it doesn't, it's not concerned with both of my inputs being a 1. And so here I get both inputs as a 1. I still get a 0 out. And that's my NOR gate. Here you can see how the OR gate and the NOR gate truth tables are just the opposite: 0, 1, 1, 1, and 1, 0, 0, 0. So they're completely opposites of each other. That bubble inverter just takes the output of the OR gate and turns it to the other state, from 0 to a 1, from a 1 to a 0, and does that for everything. And then finally, we had our XNOR. Remember, the XOR was when we wanted either input a 1, but not both. And so what this says now is that either input, but not both, is not F. So A or but not both B equals not F, right? So anytime this statement is true, it's going to be not F. The other way to think about that is, as I go through my XOR, and then I have the bubble inverter that is just going to invert what the output would typically be for my XOR. Typically, any input that was a high would give me a high out, as long as both were not high, right? That was typically what we would see for the XOR. What that means now is that anytime I have a high input, which would typically be a 1, I'm going to get a 0 out. When both are high, I'm going to get a 1 out. Or when both are low, I'm going to get a 1 out. Right? So 2 zeros, which for an XOR, 2 zeros would give me a 0 out because neither are high, but it's inverted, and so I'm getting a 1 out. 1, it's inverted, so I get a 0. This 1 typically be a 1 for an XOR, it's inverted, I get a 0. And then the XOR is where we said if I get 2 1s, if I get all of my inputs 1s, then I want a 0 out, but it's inverted for the XOR, so I get a 1 out, right? You can see the difference in the tables here. 0 1 1 0 for the XOR, 1 0 0 1 for the XNOR. We talked about having 3 inputs. Nothing changes with 3 inputs other than just having another input and having a larger truth table. Remember the formula 2 to the n, where n was the number of inputs, is going to give me how many unique combinations I can have and how many different outputs I can have. So it's just a larger truth table, but the rules are still the same. For an AND gate, if I have more inputs, I'm still, in order for me to get a 1 on my F, to get a 1 out, all of my inputs have to be high or 1s, right? Same thing with an OR gate. If I've got an OR gate, in order for me to get 1 out, one of my inputs, A, B, or C, have to be high. We looked at how we can combine these gates together. We can start taking OR gates and AND gates and combine them in this connection of gates to start making larger expressions. And so here we have 2 OR gates that are ANDed together by an AND gate. So A or B and C or D. Basically what that says that I'm going to have to get, in order to get high out of this, I've got to have at least one of these inputs high and at least one of these inputs high. Either one of these being high or either one of A and B being high will give me a 1 and a 1, and that together I'd get a 1 out. Anything other than that, right? If I had, all zeros, or if I had, a low on C and D, if I get 0 out of either one of these OR gates, then I'm not going to get a 1 out here. So that's just one combination. Here we took a couple of AND gates and we ORed those together, right? And so that means that we would have to have A and B, or C and B. Either both of these or both of these are going to have to be high, so that I get one input that's high to give me a 1 out. All right. So just wanted to kind of go back and take a look at those gates, quickly run back over those before we get into some of our, I think we're headed toward binary tonight, doing some number conversions. But just to remember why we're talking about digital and what we're going to be using this, some of this math to actually do for us. So let's see. Now, some of the stuff we're going to talk about in terms of number conversions, the good thing is we already know a lot of it. Even if we don't know binary or hex or decimal, we already know a lot of it because we're so used to working with base 10, right? And so we can take what we know with base 10 and really help us along with these other numbering systems. And so we're going to take a look at binary, octal, and hexadecimal. We're going to take a look at doing some conversions between binary, octal, and hexadecimal, and just working with those numbers. All right. So what do we know about decimal? Decimal, our base 10, what we're always working with, it's what we feel comfortable working in, right? A couple of things that we know. First of all, we're saying base 10. We know there's 10 unique characters, right? 0 through 9. So that gives us 10 unique characters for base 10. Well, we're going to be able to carry that forward. We already know base 2, binary, bi meaning 2, base 2. Well, base 2, there's 2 unique characters, a 0 and a 1, right? And so we have to remember when we're thinking about, this numbering system, we can't forget 0, right? It's easy to remember 0 in binary. Sometimes, we get accustomed to kind of setting it aside for some of our other numbering systems, but everything starts with 0 through 9, 0 through 1, or as we'll see in hex, 0 through 15, and 0 through 7 for octal, right? And so all of that remains true just like it is in binary. The largest value in a position on the number line is always 1 less than the base, right? So basically what is that saying? Well, basically, when I'm working with base 10, the largest value I could have, like, let's say right here, which we know is our ones column, is the number 9, right? That's the largest number we can have. That's the highest unique character before we go to the next weighted column. Let's see, if the positive positions in the number hold the line maximum, the sum. Okay, so what they're saying there is that if we would put the maximum value in each one of these weighted columns, it will always be 1 less than the weight of the next column. For example, what I just mentioned here about 9, if we had a 9 here, well, that's 1 less than the weight of the next column, which was weighted 10, right? If we had 99, so a 9 in the 10s column, a 9 in the 1s column, well, that's 1 less than the next weighted column of 100. That's all it's saying. Now, like I said, I know this is really, really, really basic for decimal because we're so used to it, but that same rule holds true in all of these numbering systems. When we get to octal, when we get to hex, all of that still holds true. Here you can see where it's showing us a couple of those things. This is where we talked about 9. It's 1 less than the next weighted column of 10. Here we've added 9s together. We put 9 in each one of these columns. So this is the 10,000s, the 1,000, the 100, the 10, the 1. And so we add all of that together. We do this automatically. We're so used to it that we don't even see this kind of, we don't think in this term anymore. We think immediately with this number, 99,999. But the point is, you can see that the sum of all of those 9s is 1 less than the next weight, right? When we have the max value, it's always going to be 1 less than the next weighted column.
Hey, Troy. I got it. I get it.
All right. Now, if we're talking about conversion, right? So converting 44 base 10, and it's worth noting that when we talk about base 10, right? When we actually put this number out here as base 10, the reason we're doing that is so that you'll know it's binary, because we're going to get into some of these numbering.
Probably why it broke.
I'm picking up somebody. If you guys could mute.
Time. It's supposed to be this way more. It's like out of true. But this one is super fucking stiff.
Hold on 1 second.
Like, this is where it catches when.
All right, so let me go back and all right, so when we're talking about base 10, the reason we're going to do that is just so that you know it's base 10, right? And I'll tell you, if we have a number like we have 44 here and there's no base identified, well, that's base 10, right? Because if we're going to give you, you know, if it's going to be hexadecimal, then we've got to make sure that we identify hexadecimal. You know, so just be aware that we're typically going to identify the numbering system as we did here, given it a subscript. But if there's no subscript, then it's what you're always used to. It's decimal, right? And so what they're looking at here is converting this 44 to binary. Now we know binary is all ones and zeros. Gosh, I feel like we missed. Hold on a second. Let me just check some things here. I feel like these slides are out of order, but
don't we need to list the binary the 0, 2, 4, 8, 16?
Yeah. You'd think you'd start there, right?
Yeah.
But we'll go with this and we'll see where we wind up. Yeah, because just like we talked about with our decimal in terms of those weights being, you know, 1, 10, 100 of each of those values, the same thing holds true with binary. In fact, let's just, it's got to be in here. Let's skip ahead and just, here we go. Let's just take a look at this, right? And so when we're looking at binary, if we're right here at the decimal again, right? And remember, you know, anything, basically what we've done is we've taken this base and we've raised it to an exponent. You know, we took 10, we raised it to 0, we get 1. Anything raised to a power of 0 is always 1. And then we took 10, we raised it to the power of 1, and we got 10. 10 raised to the power of 2, we got 100, right? And so we got our weights. That's how we got our weights. We're going to do the same thing here, but our base is 2, right? And so we're talking about a binary numbering system. Our base is 2. We've got 2 unique characters, a 0 and a 1. And so we figure out our weights. Well, 2 to the 0, that first column is worth 1, which is, you know, always going to be the case. Then the next one is the base raised to the first power, so 2, base squared, 4, base cubed, that's 8, base to the 4th power, 16. And you can see what's happening here. Because we're working with 2s, we're doubling each time, right? So we start with 1, it goes 1, 2, 4, 8, 16, 32, 64, 128, and it's going to keep going. And it's pretty easy to recreate these weights because it does double each time, right? And so that's when we're thinking about the conversion that we're going to go back to here in a second. What we want to do is we want to figure out what combination of these weights do I have to put together to get to that value of 44, I think it was. And so if we go back and we look at 44 binary, there's a couple ways you can do that. There's a couple ways you can convert it to binary. And one way is to just divide by the base, divide by whatever you're trying to convert to. So we'll divide by 2. And what we're going to be paying attention to is that 0, the remainder, right? And so what happens is we take the number, we divide it by 2, and it's an even number. So 2 will go into it evenly, 22, and we get a remainder of 0, which tells us there's no 1s, right? Because we're going to put that in the far right column. You know, this would be the decimal right here, to the right of this last zero.
Hey, Mike.
Yes, sir.
I got a quick question. Are we trying
Sure.
to figure out the binary sequence for 44?
Yes, you are.
So how can it be zero? Is 44 going to be 101100?
Yes.
So that's
Yes.
going to equal 44.
That's going to equal 44.
Okay.
Absolutely.
Okay.
Absolutely.
Sorry.
No, you're perfect. And we start off, the first thing you think here is, well, wait a minute. Okay, this zero, this says I don't need any ones, right? And before I go to make that comment, let's just go through this process, and then we're going to go back to the chart where we got the weights, and then we'll add it up going in the other direction, right? And so basically what we're doing here is we're dividing by 2, and we are looking at our remainder. And so I get 44 divided by 2, which gives me 22 with a remainder of 0. The 0 is that remainder is what I'm paying attention to. So I've got no ones. I put a 0 down. I've got 22. I'm going to divide it by 2. This is just, continuing to go through this process of divide by 2, which gives me 11. Once again, it goes in evenly. So therefore, I've got no remainders. So I get another 0. Now I'm dividing 11 by 2. I get 5, which is a total of 10, but I've got a remainder. So I'm going to take that 1, and I'm going to bring it right down, and I'm going to place it here, right? I'm going to do the same thing. 5 divided by 2 gives me a remainder of 1. 2 divided by 2 gives me 1 with a remainder of 0. And then 1 divided by 2 gives me a 0 remainder of 1. And so here's what I get: 1 0 1 1 0 0.
Mike,
if we, yes,
sorry.
sir.
I think I don't know if this seems confusing to me. If you write out the chart, 1 2 4 8 16 32 64, but you look at 40, you look at 44, 32 can go into 44.
Exactly.
So you put a 1, and then exactly. And then the 8 is going to be 40, and then the 4 is going to add up to 44, so it's going to be 1 0 1 1. So the way you have it written out here is kind of confusing to me.
So there's 2 ways. There's 2 ways to do this, and usually the way that you're going, that's the route that's easiest to go, right? And so I just want to go through this process just because when we get into octal and we get into hex, it might be easier to go this direction. However, from binary, what you're doing, we're talking about our weights: 1 2 4 8 16 32. Well, yeah, 44, the biggest number that will go into it on this this lumbering line is 32. The next number was 64. So 32, what I'm talking about here is really 32 plus 8 plus 4, right? 32 plus 8 is 40, plus 4 is 44. And so we'll do it that way as well, right? Now here, this is, and they just want, I think they just want to show you this. So don't get caught up on this binary or even this octal, or they just want you to see it, right? We could take that same 44 and we can convert it to octal by using the same process, right? And while we could still do the same way, we could take a look at our weights and which column would go into this number the easiest, right? We could still do that same way. It's just a little bit more difficult with octal than it is with binary. Binary is so easy just to say, hey, we're talking about 1 through 512 or 1024. We could list that off very quickly. It becomes a little bit more challenging with our octal, but the same thing works. If we're talking about 44 decimal, we're going to convert that to octal. Well, we could divide by the base 8, which is octal. It goes in 5 times with a remainder of 4. We drop the remainder down. Now we got 5. Well, that was a remainder. So 54, right? Now that would be 54 base 8. Well, that's still 44 in decimal. And then they're showing that you could do the same thing here with hex. Hex, being base 16. 44 divided by 16, 2 is 32. So that leaves me, what, 6 left over. And so we get a C. We'll talk about what that means. And so they're just showing you this process of you can take binary a decimal and convert it to any of those different numbering systems by just dividing and using the remainder and working it from right to left, closest to the decimal out, and you would have the number, the corresponding number. Now, the easier way to really do that, especially when you're talking about binary, is to go back to this numbering system, this numbering line, and better understanding what the weights are, right? Really, diving in and saying, okay, I know that the decimal is here. Remember, here's my exponents, 0, 1, 2. These negative exponents, meaning I'm going less than 1, right? So that's going to the right side of the decimal. And my weights, 1, 2, 4, 8, 16, 32. And as you mentioned, the easiest way to write this down in terms of binary, since you know these weights, if I was going to convert 44, well, I look at these weights and say, okay, what's the largest number that will go into 44? Well, it's 32. And so I put a 1 there. You take 44, subtract the 32, well, what's remaining, right? And so you just continue to move in that direction. You'd have 12 remaining. Well, 16 won't go into 12, so I put a 0 there. 8 will, so I put a 1 there. Subtract 8 from the 12, I've got 4. Okay, 4, well, I'll put a 1 there. That gives me nothing remaining, nothing left. And so I put a couple zeros in. So I've got all my weights accounted for, and boom, I've got my 44. And feeling comfortable with these weights and being able to recreate this makes it real easy to convert from decimal to binary. Here's a couple, looking at the weights, and remember what we said about decimal and what we stated was true in terms of the max character, binary being a 1. It's always 1 less than the next weighted column, right? And so here I've got 1. Well, that's 1 less than the next weighted column of 2. If I've got 1, 1, it looks like just 2 1s. However, in terms of value, remember, I'm taking a 2 and a 1, adding those together to give me a 3. The other rule that continues to hold true, I've maxed out both of these columns, and so it's always going to be 1 less than the next weighted column. Next weighted column was 4, right? So that still makes sense. And and here's where it comes in handy sometimes. If I've got all 1s, and just like in decimal, where I would take all those 9s and I would immediately add those together and give me a large value. Well, I'm going to take all those weights and I'm going to add those together, 512 plus 256 plus 128. Well, still holds true that if all of these are maxed out, then the total is going to be 1 less than the next weighted column, right? So 1024, 1 less than that is going to be 1023. That's all that is saying. If I've got all of those 1s. So we're doing the same thing that we're already accustomed to doing with decimal. It's just we're doing it with binary, meaning that we've only got 2 numbers, a 0 or a 1. We look at octal, our octal numbering system, and I'll be upfront in terms of using octal. You're going to use hex, you're going to use binary much more than you're going to use octal. But it's the same characteristics for octal hold true that we see for decimal or any of the other numbering systems. It's base 8. We're still exponents, 0 to the, or 8 to the 0, 8 to the 1, 8 to the 2. We get our weights from that. Anything to the 0 exponent, 0 power is going to be 1. The base to the first power is going to give me 8. 8 squared is 64, 8 cubed is 512, 8 to the 4th is 4096. And so you can see that it adds up fairly quickly. Same thing holds true in terms of my largest character that I can have. Remember, in 10 and base 10, the largest character I can have, the largest value is 9, 0 to 9. Well, base 8, we're talking about 0 to 7, right? And so 7 in each one of these columns would be the largest number that I could have. You see, same thing holds true. If I've got a 7 first column, that's going to be 1 less than the next weighted column. If I've got a 77 in octal, a 7 in octal, well, that's going to be 1 less than the next weighted column when I add those together. I get 63, 1 less than that, 64 of the next weighted column. Same thing holds true with more of these maxed out. Right? 4096 was my next weighted column. If I add up 7777 in octal, I'm going to get 4095. Remember, I'm taking the number and I'm multiplying it by the weight of the column, just as I do in decimal. And so I get the value 756, 448, 3584, and I would add those together to get 4095, right? Hex, same thing, right? We're talking about a numbering system now that has a base 16, just like we saw with decimal, where base 10, 0 through 9, well, base 16, that means 0 through 16, right? I'm sorry, 0 through 15, right? So my largest value that I can have is 15. The challenge with that is that if we write down 1, 5, it doesn't fall in the same category. It's impossible to ensure that you read it correctly. And so if I just put 1, 5 here, you're more likely to say, well, that's 1, 16, and that's 5 1s, right? Because you're taking up, you got 2 values there, 1, 5. And so I've got to represent that with letters as opposed to numbers. And so we're talking about base 16, so hexadecimal, we're going to go 0 through 9, just like we did with decimal. And then 10 is going to be A, 11 is going to be B, 12 is going to be C, D is 13, E is 14, and F is 15, right? So the largest value is going to be 15 that we're going to represent with Fs, right? So if we see an F, then we know that's the same as 15 in hexadecimal. We once again take a look at if this is maxed out. And so I've got an F here that's maxed out. And so it's 1 less than the next weighted column. 16, that F is 15, right? If I had 2 Fs, that's going to be 15 times 1 or 15, 15 times 16. I add those together and I should get 255, 1 less than the next weighted column, right? We see that here. F is 15 times 1 gives me 15. FF is 15 times 1, 15. 15 times 16 or 240. That together is 1 less than the next weighted column of 256. Same thing holds true down here. F. It's going to be 1 less than the next weighted column. So 65, 5, 3 instead of 6, 65, 5, 3, 5. You can see these numbers will get extremely large fairly quickly. Okay, so we're going to use some of these numbering systems to represent our be able to really, just as we did in the beginning, we were talking about scientific notation, and we were talking about how we use scientific notation to represent numbers that are either really large or really small. It helps us, as you know, to deal with the numbers. Well, some of this is true as well, because when we start thinking about binary, you know, we're going to talk about some binary numbers that is a string of ones and zeros that it's impossible for us to interpret all of those ones and zeros if it's just a long string of ones and zeros. You know, it's easy to deal with ones and zeros if they're, you know, we're talking about, you know, in nice packages of 16 bits, but when we're talking about, you know, a bunch, it becomes very challenging for us to figure out what in the world that is. And so we can go in and we can use a conversion to convert binary to hexadecimal to give it some context to allow us to better understand what that number is, or at least allow us to better document what that number is instead of, you know, all the ones and zeros. And so we're going to talk about how do we convert back and forth, you know, how do we move from one numbering system to another numbering system. And we saw how we could take a decimal number and we could just start dividing it by, you know, any one of these bases and use the remainder as a way to, you know, kind of chart it on a number line so that we had a value of, you know, decimal going to binary, or decimal going to hex, or decimal going to octal. But we're going to look at some other ways that we can make that happen as well, and often easier ways to make that happen. So we're talking about converting a binary number to decimal. You know, it's pretty easy when we know the value, the weights, right? And so if we were going to convert 1011 to decimal, you know, it's just a matter of us understanding what the weights are and then adding those weights together, right? You don't have to, at first, I won't say that it's not helpful. You know, it's helpful to be able to recreate this number line, but it doesn't take long before you're able to just say, okay, I know the values of these binary columns just based on, you know, 1, 2, 4, 8, right? And so I can start here and just double 1, 2, 4, 8, and I can begin to add those up to figure out what the value is going to be. You know, it's just a matter of adding up where I have the ones, right? It's going to be just like we did before. This was a weight of 1. Well, I've got one of those. So 1 times 1 gives me 1. 1 times 2, I'm going to add that. 1 times 8, I'm going to add that. You know, the zeros, I don't have any of those weighted columns, and so I don't add anything there. And so for this number, I'll be adding 8, 2, and 1. That's going to give me 11, right? And so that means that this number, the 1011 in binary, is 11 in decimal, right? And so it is the number, the decimal number 11. Everybody see that? I'm just looking at the weighted columns and adding up where I've got my ones. Okay. Once again, they've put the base, this subscript here, just so you know that it is binary. Keep in mind 101101 could be a decimal number, right? That could be 101,101. However, we know that this is a binary number because it's got a subscript of 2. If we're going to convert that to decimal, all we have to do is go through and do this process again. You know, we know that as we look at this number, we're talking about a 1, a 4, an 8, and a 32, right? So I can add those together. 32, 8 is 40, 44, 45, right? You see that's what they've done here is they've taken the columns that they've got a 1 in, 32, what's weighted 32, what's weighted 8, what's weighted 4, what's weighted 1, to give us a total value of 45. So it's pretty easy, right? It's not that difficult. It's just a matter of some simple addition and making sure that you get the weighted columns right. Now we've got 427. This is octal. We're going to convert that to decimal. You know, this number, this weighted number line works well when we're converting to decimal, because that's basically what we've done here is we've created this weight, right? So this is the decimal equivalent, if you will. And so if we're going to convert, I don't know why they put this. I think this must be left over from the last graphic. But when you put 427 on the line, right? So 427, that means I've got 7 ones. It means I've got 2 of the 8 column. Remember that was 8 to the 1, so 8, weighted 8. And I've got 4. This was 8 squared or 64. So 4 times 64 or 256. I add those together. 256, 16, and 7 gives me 279 in decimal. Right, 279. Once again, it's the same process. It's just a matter of making sure that you get your weights right. And the weight's always the base, raised to the 0 power, raised to the first power, raised to the second power. And so really, you know, since we know that, we could really work within any numbering system we wanted to. Here we've got a hexadecimal number. So a base 16, you know, 14B, right? So 14B. We know that that B represents 11, right? And so we do the same thing. We got base 16, 16 to the 0 is 1. You know, the next weighted column is 16, it's 256. So we need those 3 weights. For the first column, it was 1, so 1, 256. We've got 4 16s, and then we've got B, which we said was 11 in the ones column. We do the multiplication, and what do we get? 256, 64, and 11, for a total of 331 in decimal. So we converted a hexadecimal number to a decimal number, 331. Yes. Yeah, and so really it's a matter of, you know, in hexadecimal, meaning that I've got 0 to 15. 15 is my largest character, right? Like in decimal, we had 0 to 9. It's always 1 less than your base, hexadecimal being base 16. So 15 is the largest number that I can have. The only thing is I can't write 15. Like if I put up here, instead of B, if I put 15, we're going to read that as taking 2 weighted columns, right? We would read that as 1, 4, 1, 5. And we would try to put 5 in the ones column. We would try to put that 1 in the 16th column. And so we had to figure out a way, how do we keep that within 1 weighted column? And so the easiest way to do that, what they do in hexadecimal is, well, let's just go to the first alphabet, the first of the alphabet, and the first number that takes up 2 spaces, which is 10. So we're 0 to 9. The first letter that takes up, or the first number that takes up 2 spaces would be 10. Let's give that a number. All right, give that a letter. Let's assign that a letter. So let's assign that A. And we just follow that all the way up to 15, right? And so it's going to be 0 through 9. And instead of 10, it's going to be A. B is 11, C is 12, D is 13, E is 14, and F is 15. That makes sense? Yeah, like I said, really, the reason we're doing that, if I tried to write this number on this number line, and I said, okay, instead of using B, I'm going to use 11, which is B is what B is equal to, then I would write on this number line a 1, a 1, and then 1 4. And so you can see that's a very different number, right? If I had 1 4 and instead of B, I had a 1 1, because it's hard to tell, is 1 1, does that mean 11 as B, or does that mean just a 2 1s? And so what we had to do is we had to differentiate between what is 11 and what is, you know, 2 numbers. And since we couldn't use those 2 numbers, I mean, there's just no way to identify that as only being 1 weight. You know, the nice thing about decimal or even octal or binary, you never have a number that's 2 digits. And so everything falls nice and neat in these categories, right? So we've got this weighted category of the base to the 0. And so, you know, the largest values I could have in decimal was 9. Well, that doesn't take 2 categories. And so I can easily put a 9 in. You just can't do that when you get into double digit numbers, when you get into 10 or 11, 12, 13, 14, 15. And so we just start off with A, and we just say, hey, A is 10, B is 11. We're just going to assign it going A through F, those numbers that are double digits, you know, 10, 11, 12, 13, 14, and 15, and know that F is going to be the largest, represent the largest number that you can have in hex, right? So we see a base 16, we see that letter, you know, if it's A, it's going to be 10. If it's B, it's 11. You know, it's just as simple as thinking about, okay, what's my first double digit number? Well, 9 is the last single digit number. 10 is my first double digit number. So 10, 11, 12, 13, 14, and 15, A, B, C, D, E, and F. So we're just assigning those letters. And then, you know, from there, I'm just adding up, right? I'm adding this B, which is equal to 11. A was 10, B is 11. Adding those weights. 11 times 1, that gives me the value of 11. 4 times 16, 64. 1 times 256. And I add all that together to get that 331 for base 10. That's what it's equal to in base 10. You know, here's the method that you talked about in terms of converting binary and using the number line to convert binary. I'm sorry, to convert decimal to binary. Once again, 44. This is typically the way you're going to do it, just because you get to the point where you feel comfortable with the weights. It's real easy to start with the largest weight that will go into that number. You know, here, 32, what's left, and we just begin to work from there. You know, and you know, once you begin to feel really comfortable, you're going to say, okay, 32, I subtract, I got 12 left. Well, I know that's an 8 and a 4, right? And so you write down where you need ones, everything else is zeros to give you that number that you're converting from decimal to binary. And that's, you can see that's what they're doing here. Didn't need a 16. 12 minus 8 was 4. Right, so we had an 8, we had a 4, and then no 2s, no 0s to give us our base 10, 44. Well, we've seen that before, is 10, 11, 00. 10, 11, 00. The great thing about these number conversions, you can always check them, right? You can always go back and do the math and make sure that they convert one way and back the other. You know, if you convert, let's say you converted 44 in decimal to binary, and then you go back and you add the weights and it doesn't add up, something's wrong. You made a mistake somewhere. And so there's a good way to check it. You're going to octal, you could do the same thing, right? We could take a look at the weighted columns for octal. For hexadecimal, we could do actually, hold up a second. I want to see if, yeah, okay. So let's do this. So in terms of binary, if we converted that 44 base 10, we got 101 100. That's what we said was 44 in binary, right? And then what we want to do is we want to convert that binary, that 44, to octal. Let's say that we're going to go this binary number. We're going to convert that to octal. We're going to create a number that's maybe a little bit easier for us to represent. Instead of 6 binary bits, let's change it around a little bit and let's work within octal. Like I said, you're going to do this more with hex than you will octal, but we'll just do it with octal so that we can understand how to do it. Now, the thing to remember about octal, what was the largest number that you can what's the largest number in octal? Yeah, I asked that I asked that wrong. I asked that wrong. Yes. So what I was looking for, what is the largest character, single character in octal? Yeah, and I heard somebody say 7. Yeah, right. And so I want to share. Yeah. So the value of each weighted column would be 8, 64, exactly like you said, because that's taking the base and it's going to the exponent of 0, 1, 2, 3. So base to the 0 power is always going to be 1. Base to the first power for octal would be 8. So that's the weights of those columns. That's exactly right. Just like in binary or in decimal, we take 10, right? Base 10. And we say, okay, 10 to the 0 power. Well, that's 1. So we got the ones column. And then we go 10 to the 1 power. Well, that's the base 10. That's the 10 columns. And then we go 10 squared. That's 100 column. And so we feel really comfortable working with those weights. But think about the numbers that we put in each one of those weighted columns, right? If I'm going, what's the largest number I can have in decimal to fill one of those weights, right? So if I have, think about the ones column, all right? The ones column, I could have a 0, a 1, a 2, a 3, a 4 in decimal, 5, 6, 7, 8. The largest number I can have is 9.
Are you right?
9.
Are you right? I don't see anything on the screen.
Is 7. Yeah. Yeah, so it is base 8. It's base 8. Octal is base 8. I want to get back to this chart. I'm going to share this with you. Just like decimal is base 10, right? If we're talking about decimal, we put a 10 in here. We say 10 to the 0 is 1, 10 to the 1 is 10, 10 to the 2 is hundreds, and that's how we get our weights, right? Our ones, our 10 place, our hundreds, our thousands. And then, but the largest number for decimal we can put in here is a 9. Right? We don't put, because 10 goes to the next column, right? That's a 1. That means we've got in a base 10, that would be, this is the tens column. So I've got 1 10 and I've got 0 ones, right? So it'd be a 10 and a 0 give me 10 for decimal. Same thing holds true here. It's a base 8, right? And we're going 8 to the 0 is the 1, 8 to the 1 is 8, 64. So you got the weights perfectly right. The numbers will always be 1 less than the numbering system. So the largest number that we can have will be 1 less than the base. Base 8, that means 8 unique characters. Don't forget 0. So we count that, right? 0, So we've got 8 characters, but in order to get 8 characters, I can only have the largest number can be a 7. Because if I included 8, because I'm counting 0 as 1 as well, that would be 9. That sounds confusing as can be, but you understand what I'm saying? Yeah, because if we count 1, 2, 3, 4, 5, 6, 7, but don't forget we got to count 0 as well. So it's 8 Yeah, base 8, right? It's always the base, right? And so the if it's octal, it's base 8. We're going to figure out the weights, but we have to remember that the largest value I can have is going to be 1 less than the base. So if it's base 10, the largest value I'm going to have is going to be a 9. If it's base 8, the largest value I'm going to have is going to be a 7. If it's base 2, the largest value I'm going to have is going to be a 1, right? Because you got 0 and 1. If it's base, if it's hexadecimal, which is base 16, well, the largest number is 15, which I have to represent with an F because, if I start trying to put a 15 in here, it's going to look like 1 character's in a different column, right? So that's why we go with that letter, so we can still get it into 1 column. So yeah, you're exactly right. Don't, the base is what it is, right? And we identify the numbering system by the base. Base. So decimal is base 10. Octal is base 8. Hexadecimal base 16. Binary base 2. So we work out all the weights based on the base itself, raising it to the power of 0, 1, 2, 3, 4, and that's true for any numbering system. Then the only trick we have to remember is don't forget 0. That's why we're always 1 less here, because we got to count 0. That means we're going to be 1 less than the base is going to be my maximum value, right? So let's go back and let's take a look at we were about to convert from binary to octal. But before we do that, I just wanted to do something. Let's see if I can. All right. Going back to that notion of the largest value you can have in octal, represented by 1 character, is 7. What I'm going to do, if we think about that, what we can do is we can let me ask it this way. So what is 7 in binary? If I was going to convert the number 7 in binary, what would that be? There's a couple ways I could do it. I could think about, I already know the weights, right? Binary 1, 2, 4, 8, and so I could work through what numbers do I have to add together to get 7. What do you guys think?
1, 1, 1.
Okay, 1, 1, 1. Okay, 0, 1, 1, 1. All right, and in reality, in terms of that first 0, do I really need that first 0? I don't. I only, in order for me to represent 7 in binary, I've got to have 3 bits, right? Yeah, 3 bits. 1, 1, 1. So 7 base 10 is equal to in binary 111. Right? That's what we're saying. Now, the only reason I wanted to make that clear and to just think about binary for a second is what we're going to do is we're going to convert from this number, this binary number, we're going to convert that to octal. Now, what we can do, the easiest way to do this is to then look at if it takes 3 bits to represent 7. 7 is the largest number I can have in one binary. One octal value. Largest I can have is 7. What that allows me to do is to take this binary number and split it into 3s. I'm going to start at the decimal. I'm going to work back to the left, and I'm going to split, 001, really left to right. I'm going to, or right to left. I'm going to split it just like I've done here. 001. I'm splitting that 101. And the reason I'm going to do that is anything that the reason I want you to do it that way is this just happened to be 6 bits. And so it works out nice where if I went from left to right, I split it, or if I went from right to left, I split it. But what you need to do is you need to start to the right and move to the left, because if this was an odd number of bits, you may have to add another binary bit to the left of this, add a 0 to the left to make it work out. So I'll give you an example. After we do this one, I'll give you an example as to how that would work out. But let's just start at the decimal. Let's move 3 binary bits. Let's break that. Next 3 binary bits. And we know that those 3 binary bits, the largest number that you could have in binary with 3 bits, 111, you guys told me was 7, right? Well, that's the largest number you can have in octal is 7. That one representation would be 7. And so it works out where we can divide or can split this binary number into 3 pieces or into 3 bits. And now I'm only working with those 3 bits, right? And so I'm looking at, if I looked at the weights, 1, 2, 4, right? And so that's going to be a 4. Well, in octal, it's still going to be a 4. Right? That's all we're doing is this is going to be a 1, 2, 4. So I've got a 4 and a 1. So that gives me a 5. And so this binary number 101100, by splitting it into 3 bits and 3 bits, and then only treating those 3 bits as equal to a value in octal, right? I get 54 octal is equal to 101100. I'm sure that's clear as mud, but the big thing to see there is that because of the way octal is weighted, and because of the fact that the largest number I can represent in binary in 3 bits is a 7, right? If this was a 1, 2, 4, so a 4 and a 2 is 6 plus 1 is 7. You guys told me 111 is 7. And so that means that I can take these 3 bits, and those 3 bits will be represented by this 1 bit in octal. And then I just do the conversion. And I can continue that on. Now we can do the math. Let's just make sure this still works out. If we're looking at octal, we said this was the 1s column. This was 8 to the first power. So this is the 8 column, right? So 8 times 5 is 40. This was the ones column. So plus 4 more. That's still 44 in base 10. All we've done is we've taken this binary number and we divided it into threes. Now, just to kind of give you an example of what I was talking about in terms of dividing it at the right spot. Let's just say instead of 1 0 1 1 0 0, let's say we had I don't know, 1 1 0. Oh, it's hard to draw with this. 0 1. All right. So let's say we had that number 1 1 0 0 1, and we were going to convert that to octal. Now, what we would do is we would start once again where the decimal's at, go 3 places, 1, 2, 3, and so I treat those 3 bits. Right, I would divide it, and this is not another 1. I'm just dividing it, right? So I would treat these 3 bits, and then I would go over, and notice there's only 2 bits here. Well, what I'm going to do is I'm going to just put a 0 here. That doesn't change the number at all. It just allows me to say, okay, I'm representing this side 3 bits, this side 3 bits, but I start at the decimal. If I would start the other way, while it worked out for this number because there were 6 bits, if I would start the other way over here and went 3, then I would represent those 3. And I can't draw a 0 there because it's going to change all the weights. Everything would shift to the left. And so it's going to change the value of the number. So I start at the decimal, go over. That's where I'm going to start. There's my first 3, my next 3. It could be a larger number. I mean, it could be more than just 5 or 6 or whatever numbers. But I'm going to separate here, and then I'm going to treat each one of these as a 3 bits, converting those to octal. So what would that be in octal?
$31.
31. Okay. Anybody disagree with that? Right. So we said, okay, this is going to be 1, right? Way to 1. And remember, we separate these out, and when we separate them out, we treat these 3 as 3 unique bits, and then we do the same thing here. So once again, even though we know if we're looking at binary, it's going to be 1, 2, 4, 8, right? But when we separate these, we just go ahead and convert these, treat these like 3 unique individual bits. And so that's going to be, a 1. Those 3 would be a 1. This would be a 3, like you said, because we're going to put a 0 here. So that's 31, and that's base 8. If we go backwards and we do the math, that would be 1, 1. That would be 3 eighths. So that's 25. Is that right? Am I doing the math right? 25. Let's see if that works out. Let's see if that works out up here. So 1, 2, 4, 8, 16. So 16 and 8 is 24, plus 1 is 25. Okay. Yeah. So the big thing there is just to, it's a quick way to convert from binary to octal, just to know that you can look at the largest number in binary represented by 3 bits is 7. Well, that's also the largest number that can be, the single character in octal. And so that way you can divide it into 3s and go from there. Before I go to the next slide, This is kind of, let's see. I'm sure it's on the next slide. So if we said that in terms of octal, the largest number I can have was 1, 1, 1, which was equal to 7, right? I guess might as well put an equal mark there. And so we could take a binary number, convert it into 3 bits, start separating it from the decimal working to the left, and I can convert that to octal and it would work out. What could you tell me about hex? Is there anything that we could do along these lines that would be similar for hex?
Take 6 of them.
Take 6 of them. Okay. All right. How'd you get 6?
Because it's 8 and 16, and then you're just doubling it. So
Oh, okay. Okay. I see what you're thinking there. All right. Think about what we did here in terms of binary and the value of these 3 bits, the largest value we could have, including, equal to the largest value we could have in octal. What's the largest value we could have in hexadecimal? 15. Okay.
so it'll be 4.
Oh, how did you get 4?
Because it's 16, 8, 16. Or so it'd be the 4th column.
Everybody agree with that? We do a little math. 1, 2, 4, 8. So 8 and 4 is 12, plus 2 is 14, plus 1 is 15. That's the largest value we could have in hex, 15. And we know we're going to represent that with an F, but we're the number 15. So what do you think that means for us when we're talking about converting binary to hex? We went binary to octal. We took a binary number and we said, hey, let's just separate it into 3s, and then we'll treat it like, we would normally, each one of those 3 bits, and come up with our octal values. We're going to be able to do the same thing with hex. The only difference is, instead of dividing it into groups of 3, we're going to divide it into groups of 4. That makes sense? I mean, if the largest number that 4 binary bits can represent is a 15, and the largest number I can have that's represented by 1 hexadecimal value is 15. So therefore, I can just divide this binary number by 4s, into 4 binary bits, and then I can treat that, each of those 4, use that for translating into hexadecimal. So let's see that. Do I have any Tylenol? Oh. And so all that's saying is, once again, we're talking about that hex. Decimal 44. We've already done that conversion, and so we start here with this number that's 44. When we're going to octal, we divided it into 3s. Well, if we're going to go into hexadecimal, the largest number that can be represented, you guys said, was 15, which is 4 bits. So let's divide this by 4, right, into bits of 4. We're going to start with a decimal, and we're going to work to the left. So 0, 0, 1, 1. And then we're left with 0, 1, but we're going to add a couple of zeros just so it works out. That doesn't change the value. Those zeros, remember, we don't add those up. And so it's just giving us those 4 bits that we can work with. You can see that's what we get here, 0010 1100. Now, all we got to do is just take each one of these and convert it to the corresponding value in hex. You know, what's this number in decimal?
12.
12, right? 12 was one of those, that's a double digit number. And so we can't just write 12. You know, we know 9 is 9, 10 is A, 11 is B, so C is 12, right? So we got to write a C. And then what's this? 0010.
2.
2, right? So our number is 2C. Base 16, hexadecimal, 2C. Right? That was supposed to be 44. We know the weights in these columns because it's hexadecimal. You know, this was always to the 0 power. So this is going to be weighted ones. This is going to be 16 to the 1 power. So this is 16. 16 times 2 is 32. 32 plus 12 would equal 44. Yeah, so it's still a decimal 44. It is a binary 101100, and it is a hexadecimal 2C. But you guys never thought you'd see that, the summary page.
I need an octal break.
In an octal break. Oh, so yeah, it is a good time for a break. Hold on one sec. Let me see. Okay. So I tell you what, you guys have been working hard, doing good. Let's take I've got half past the hour. We'll take a 15-minute break. All right. Come back at a 1:45. All right. Just wanted to mention there is a practice number conversions in the course. You go in, select that, and it gives you a couple of tables, an opportunity to convert between each of the numbering systems that we've talked about today, and then it gives you the answers on the next page. So I would recommend going and working through that practice so that you've done that a little bit. Let's take a look at this. This is just an opportunity to once again hear this in a maybe a little bit different light. It's always good to hear something from a different perspective.
What is going on, everyone? My name is Codemore, and welcome back to Electronics episode 27. In this episode, we are going to learn about the binary number system. Now, if you already know binary and you're really comfortable with it, you can feel free to skip this video. But if you don't know binary very well, I highly recommend watching this video, because when we make our 8-bit computer, we are going to be using binary for literally everything. Our computer commands are going to be binary, all of our numbers are going to be binary, all of our math is going to be in binary. So you really have to begin getting comfortable with this binary system. And we will have plenty of practice with this as we go along with this series. Now, I've found that the easiest way to explain binary to someone is to start with what we already know. And for the most part, we all count in base 10. So what exactly does base 10 really mean? Well, for starters, it means that we can use the digits 0, 1, 2, all the way up to the digit 9. So we have 10 total digits, 0 through 9, to work with. The next important thing to note, and this is something that we do without even really thinking about it, is that the position of each digit in base 10 in our numbering system has a very specific meaning. So if we have the number 8, well, we know that's the value 8. But now let's take a look at the number 1, 8. Now, if this number 1 was on its own, then it would only represent, well, the value 1. But this 1 is in the left position. It's in the second position over in this number. And obviously, we know this as the number 18. So basically, whatever digit is over here to the left really doesn't represent 1 anymore. That represents that we have one group of 10, essentially. So this really equals 10, and then we add on our single digit 8 here. And of course, that gets us, well, the value 18. It's sort of hard to write it like that. And of course, as you move further over, if there was another digit here, well, this would actually be worth 100 times whatever the digit is here. So if there was a 2 here, well, this is worth 200. And then you'd add that to the rest and you get, well, 218. It's really easy for us to overlook these simple little things because we do it automatically in our mind all of the time. So let's really quickly break this down into more of a mathematical formula. Say we have a number that's worth three digits. Say we have a 3-digit number here. I don't know, let's make it 314. The further left you go, the more significance the digit has. Then the more significant that digit is. And we can represent this using powers of 10. So the digit in the rightmost place here, well, this is worth its value multiplied by 10 to the 0. And the next place over is whatever the digit is here, but multiplied by 10 to the first power. And then more digits over, would be the digit 3, multiplied by 10 to the second power. And of course, this would continue onwards as we go more and more to the left. Obviously, 10 to the 0 here, well, that just equals 1. Anything to the power of 0 is a 1. 10 to the 1 equals, you guessed it, 10. And 10 to the 2 equals 100, of course. So in essence, what we're really doing when we see this number 314, we're really taking each of the digits, so we're doing 3 multiplied by its positional value, which is 100. Then we're adding that to 1 multiplied by 10, its positional value. And then we're adding that to 4 multiplied by its positional value, which is just 1. So of course, we get 300 plus 10 plus 4, and we get the exact same thing that we wrote, 314. And trust me, this is all going to play in to when we move on over to binary here. So we use the base 10 number system, while binary is a number system itself. It is just the base 2 number system, hence bi in binary. And if we go based off of what we learned about the base 10 number system, which was we have 10 digits to work from, 0 through 9, well, when we look at the binary system here, that this means we have the digits 0 and 1 to work with. We only have 2 digits to work with. And this is really, really great for computers and for digital electronics, because a 0 can just be represented by low, or essentially connected to ground, and a 1 can be represented by high, or essentially voltage. And this is why binary is used so often in computing and all these types of electronics, is because it's so simple to represent using voltage, using simple circuits and logic gates like we discussed in the previous video. So when you're reading binary, you kind of have to change the way that you think, and most often that results in you trying to convert from binary to base 10, something that we can really understand. So if I just have a single digit binary number, say 0, that just equals 0 in base 10. Cool, I understand that. If I have a binary number 1, that just represents 1 in base 10. Cool, I understand that. But what if I have 1, 0? Well, this is not equal to the number 10 in the base 10 number system. Instead, 1, 0 is really equal to the number 2 in the base 10 number system. So how did I figure this out? How do I know that 1, 0 equals 2 in our normal system? Well, let's take a number. Let's say, well, let me go off of what I just discussed. So we have the number 1, 0. The number further to the left is going to be more significant. Its value is going to be more than all the numbers to the right of it. So remember in base 10 when we multiplied this by 10 to the 0 and by 10 to the 1? Well, instead of doing that, of course, we are instead going to multiply these by 2 to the 0, and we'll multiply this digit here by 2 to the power of 1. And we're using 2 because, well, we're in base 2. We only have 2 digits to work from. And this is where things get not complicated, but a little bit hairy, because here we have binary, so we have 1, 0 in binary, and the multiplication that we're doing with these powers of 2 down here, well, this is in base 10. So essentially, I'm teaching you right now how to convert from binary into base 10, because that's the easiest way to begin to understand binary and to be able to recognize what a binary value actually equals in base 10. So 2 to the power of 0, again, this is just normal math as you would do it every day, of course, is 1. Anything to the power of 0 is 1. 2 to the power of 1 is just 2. Now all we have to do is multiply the digit by its place value that we assign to it. So here we're going to have 1 multiplied by 2 plus 0 multiplied by 1. Of course, this is just going to be 2 plus 0 equals 2 in base 10. So we know that 1, 0 equals 2 in base 10. And that's all there is to binary. And this is exactly how you would convert from binary into base 10. So if we take a look at the math I did here, we're doing essentially the exact same thing that I just showed over here. Only over here, our top numbers were also in base 10. And over here, they're instead in base 2. So let's do a little bit more work here with binary. Let's get a little more comfortable with it. Let's say I have a nice large number, well, not too large, but let's say I have a 5-digit binary number, and I'm just gonna try my best to write binary in base 10, that way we don't get confused here. Now let's say I have the number 1, 0, 0, 1, 1. Well, I have no idea what this means, so let's go ahead and convert this number into base 10. And by the way, right after I finish this example, I'm going to show you kind of the shortcut that I take in my head to process these binary numbers. That's a little simpler than writing out all this math all the time. Remember that the rightmost digit is just going to be it multiplied to the power of 0. This one's going to be multiplied by 2 to the power of 1. Sorry, over here I meant 2 to the power of 0. The next one over, 2 to the power of 2, 2 to the power of 3, and 2 to the power of 4. Now 2 to the power of 4 is 16, 2 to the power of 3 is 8, 2 to the power of 2 is 4, 2 to the power of 1 is 2, 2 to the power of 0 is 1. So now we know exactly what to do. We have digit 1 multiplied by 16 plus digit 0 multiplied by 8 plus another digit 0, this time multiplied by 4, plus a digit 1 multiplied by 2, and plus a digit 1 multiplied by 1. So here we wind up having 16 plus all of this is 0 plus 2 plus 1. And I'm just going to write 0 here. So this all equals 19. And that's, of course, in base 10. So we know that 1, 0, 0, 1, 1 is simply 19 in base 10 in the way that we understand numbers. Now, I'm going to teach you a really quick trick. Now, this trick might not work for everyone. This is just how my brain processes information, so maybe it'll help someone out there. My brain can pretty easily take a number and just double it. It can just my brain can easily multiply this by 2. So if I start with the number 1 on the right here, and I just start multiplying by 2, so 1 times 2 is 2, and then I continue this to the left, so I take 2 and multiply it by 2, I get 4. Take 4, multiply it by 2, I get 8. 8 multiplied by 2, I get 16, 32, 64, 128, and so on. I can do that pretty easily in my mind. So when I'm thinking of a binary number, let's get an example number of, say, 001011110. In my head, I just calculate from right to left and start adding up digits together. So I know, okay, no 1. I see a 1 here, which means I have to add 2 to my result. Okay. 1 here, so I have to add 4 to my result. 1 here, so I have to add 8 to my result. 0, so I don't have to do a 16. There's a 1 here, so I have to add a 32 to my result. That was a absolutely messed up 3. And then there's a 0 for 64, so I don't need a 64. 0 for 128, so I don't need a 128. So I know that this number is 32 plus 8, that's 40, plus 4 plus 2, that is 46 in base 10. So I know that the number 101110 is 46. So I don't even worry about all this power stuff, that just confuses me more. All I do is in my head multiply starting from 1 all the way by 2 each time as I go to the left. So we can go from binary to base 10 really easily, but say we want to go from base 10 into binary. Now there's some mathematical ways you can do this and all, but pretty much the only way I'm going to show you, and really, to be honest, the only thing that you need when we're only working with 8 bits at a time is pretty trivial. So let me write out that whole sequence of 2 I had. So 1, 2, 4, 8, 16, 32, 64, and 128. Now let me say that I have some number in base 10 that I want to convert into binary. So let's say I want to take 105 in base 10 and go into binary. What in the world would that be? Well, start all the way to the left at the largest digit that you have in your binary number or whatever. In this case of 8 bits, which by the way, 8 bits basically means we only have 8 binary places to work with. Then all I'm going to do is ask myself, does 128 fit into 105? No, so this must be a 0. Does 64 fit into 105? Yes, so it's going to become a 1 because I need a value of 64. So now I'll take my 105 and I will subtract 64 from it, and that will leave us with 41. Okay, so let's continue onwards here. Does 32 fit into 41? Well, yes it does, so that means I need another 1 here, and of course I will subtract 32 from 41 now, and this will leave me with 9 remaining. Okay, does 16 fit into 9? No, so that must be a 0. Does 8 fit into 9? Yes, so that's going to become a 1, and I'll subtract 8, and I'm left with a 1. So obviously, 4 does not fit into 1, 2 does not fit into 1, of course 1 fits into 1, so there will be a 1 at the end, and boom, I am at 0 with some crooked sideways math as I like to do, and we know that 105, that's a bad 0, 105 in base 10 is equal to 011011001 in base 2 in binary. And of course we can leave out this last 0. Any zeros to the left won't change the answer at all. And that's all I have for binary today. Now in my experience, people have kind of a hard time understanding binary sometimes, especially when you're trying to convert back and forth from decimal into binary so you can try to understand it. But I can promise you that if you do it long enough and you try and you keep working and trying to understand what these numbers mean, given time, you're going to be almost instant at converting binary numbers, or at least the small ones like 8 bits. And eventually it's just going to become second nature for you, and you're going to be able to calculate these small binary numbers and instantly know what they mean in your head. So if you're really serious about this, take some time.
All right. I know that, like I said, that was some of the same information that we just covered, but when you're dealing with number conversions and binary, you can't hear it too many times. Okay. Now, one of the things we can do with binary is we can go through the process of a little bit of binary math. We're not going to get deep into binary math, but just to take a look at, oops. Okay, hopefully you got it now. So just looking at some binary, a little bit of binary math. We're not going to go, like I said, deep into binary math, but just some rules if we were to combine some of these binary numbers, just as we do with decimal numbers. We can, have binary numbers and do some of the same math processes that we do with decimal numbers. And I have had some folks come back and say that they were asked to sum a couple binary numbers. The great thing is if you take two binary numbers, and we've talked about this before, they can't be too complex because you're going to be working without a calculator. But if you take two binary numbers and you combine those, you add those together, they should still be the same as their decimal equivalents, right? So if you had binary represented, a 5 represented in binary and a 4 represented in binary, you add those together, you should get the equivalent of 9 in binary. So it's real easy to check those. Those are almost gimmies, if you will. So just take a quick look at some of the rules for binary addition. A 0 plus 0 is 0. A 0 plus a 1 is a 1. A 1 plus a 0 is a 1. All of this makes sense to us. In rule 4, a 1 plus a 1 is a 0 with a carry of 1. Well, once again, that is the max value. You can't represent a 2, right? And typically we would say a 1 plus a 1 is a 2. You can't represent that in one weighted column. And so it's going to be a 0 with a carry of 1. And we're going to take that 1 to the next weighted column. You think about in terms of just two binary bits. If I had, the furthest right bit, a 1 and a 1, I add those together, that would be a value of 2. Well, a 2 in binary is 1 0. And so that's exactly what it's stating here. You'd have a 0 with a carry, meaning it's going to the left of 1. Here's an example of adding two binary numbers. This looks like 6, so 4 and 2. This is 5, 4, and 1. A 0 plus a 1 is a 1. A 1 plus a 0 is a 1. A 0 plus a 0 is a 0. And then here we have this 1 plus 1, right? And so that's going to be a 0, carry the 1. We said that this was 6 and 5. We would expect this to be 11. So 1, 2, 4, 8. A minute. I'm sorry. This is 10, right? 1, 2, 4, 8. 8 and 2 is 10. And this is 9. So it should be 19. Exactly. You guys keep me honest. So here, 1, 2, 4, 8. This is 116, right? So 16 plus a 2 plus a 1. So it should be 19. Yep. Guess I could always look at the bottom of the chart. So that's a nice thing about if you're asked to add two binary numbers, and like I said, you should always be able to do a nice check, right? I can easily look at the decimal equivalent, and it should be the same value, right? It should be 19 and 19.
How would you add 11 plus 11?
Say that again.
If you wanted to add, if it was 11 plus 11, how would you do that?
11 plus 11.
Yes.
All right. And so if we had 11 plus 11, 11 is 1011, right?
Mm-hmm.
And so if we had 1011, and let's do this just so we can. So 1 0 1 1 1. So hard to write with this touchpad. So yeah, here's where you, and I think this is what you're asking about. We get into our rules. A 1 plus a 1. We said a 1 plus a 1 was a what? A 0. Carry the 1. And I think this is where you're probably the crux of your question. How do you convert? What do you do here when you got 3 1s? A 1 plus a 1 plus a 1, right? So a 1 plus a 1 would be a 0, carry the 1. And then that 1 plus this, or this 0 plus this 1 is going to be a 1. So what we wind up with is a 1 and a carried 1, right? I combined these two. That gave me a 0, carry a 1. I combine the 0 and the 1, I get a 1, right? If we follow that through, this is going to be a 1. Here, once again, we got a 1 plus a 1. That should be a 0, carry a 1. So that 1 comes all the way down. And so 1, 2, 4, 8, 16. 16 plus 4 is 20, plus 2 is 22, right? 11 plus 11, so 22.
Okay, all right, thank you.
You're welcome. Okay. If we look at subtraction, once again, some of it is pretty straightforward. 0, 0, 0 minus 0 is a 0. 0 minus a 1 equals a 1 with a borrow of 1. 1 minus 0 equals a 1. 1 minus a 1 equals a 0. Right? And so rule 1, 3, and 4, typically no problems with, right? 0 minus 0, sure. 1 minus 0, a 1. 1 minus 1, 0. It's number 2 that's a little bit more challenging. 0 minus 1 equals 1 with a borrow of 1. And so let's see how that plays out. Here we have a 0 minus a 1. So we get a 1. A 0 minus a 0, that's a 0. A 1 minus a 1, that's a 0. So all of those we feel real good about. Here, we've got a 0 minus a 1. right? And so we're going to get this 1 with a borrow from the next column. We're going to have to borrow this 1, but typically what it seemed like it would be, you would borrow it, and then okay, that would be a 1 minus 1 is 0. It's going to be a 1, but we're going to take away this 1. So there's going to be a 1 with a borrow of 1. And then so we have a 0 that just falls down. So we look at those numbers, we were looking at, this says 21 minus 12, right? We wind up with 9, a 1 and an 8. So we wind up with 9. This, if you had to do this and you got confused here, like I said, that's why, that's when it's so easy to go in and say, okay, wait a minute, I know what the answer should be. Let me go figure out why I missed it. And if you typically, it will be this notion of 1 from 0 where you're going to have to borrow. Multiplication, all looks good. Anything multiplied by 0 is going to be a 0. 1 times 1 is 1. So that looks great. We're accustomed to that. It's pretty easy for us to go through and do that math, because the multiplication is the same. The only thing is, when we do this, like longhand multiplication, multiple steps, now we're going to add, and you may get back into that situation where you have multiple 1s. This is 1, 1s and 0s, 0s and 1, 1 and a 1, 2 1s added together is a 0, carry a 1. And that 1's coming through, the 1's coming through, right? So that's where we get 55. 1 1 0 1 1 1. Division, 0 divided by 1 is 0. 1 divided by 1 is 1. Should feel pretty good about that. It's pretty much the same as always. Nothing really changes here. So it's just pretty simple, straightforward division. Okay, let's go. Let's take a quick look at this.
Hello everyone, and welcome to Higher Computing for Everyone, Lesson 2.1, Understanding Binary. So the purpose of this lesson is, first of all, I want you to be able to look at a binary number and understand what the value of that number actually is. So for example, when you look at a number that looks like this, you should be able to look at it for a few seconds and say, oh, that's 6. So the way you do that is actually very easy. There's nothing hard about binary, you just have to understand a couple key concepts. The first thing that you need to understand about binary is that every binary number is made of 1s and 0s, nothing else. So with any combination of 1s and 0s, you can form any binary number that you wish. So the next thing is, how do you understand what the binary number actually is? Well, in order to understand that, you need to understand place values. When we count, if I write out a number like, let's say, 329, what I'm doing is I am placing a digit in a column, and each column has a different value. We have the ones column, we have the tens column, and we have the hundreds columns, and so on. So what we're saying here is 300, 20, and 9, and that's how we get our value. Now, this is called base 10, or decimal. That's the term for this counting system. The counting system that we use is based on the concept that every column is going to be 10 times greater than the column to the right. So the tens column is 10 times larger than the ones column, and the hundreds column is 10 times larger than the tens column. So every time you go with a new column to the right, you are multiplying the value of the previous column by 10, and that's how you get your place values. So when we count in decimal, we go 1, then 10, then 100, then 1,000, and so on, and each column is going to be 10 times greater than the column before it. Okay, so that's base 10. Binary is base 2. What that means is that rather than each column being 10 times greater than the column to the right, it's going to be 2 times greater. In other words, it's going to be double. It's going to be twice as big. So when you write out a binary number, like this for example, we can put it in columns just like we normally would. We always have the ones column, and that's true in any base, whether it's base 10 or base 2 or whatever the case is, you always have your ones column on the far right. Now, next to that, we have the base, whatever the base happens to be. In this case, since we are using binary, the base is 2. Binary is base 2. So now remember, every column is going to be twice as big as the column to the right. So we have 1, then 2. What comes next? Well, 4, because 4 is double 2. Now, why is it double? Well, that's because we are using base 2. If we were using base 10, then it would be 10 times greater. Since we're using base 2, it's 2 times greater, so it doubles. So then this binary number is just simply 2. Because there's nothing in the 4's place, there's a 1 in the 2's place, and there's nothing in the 1's place. So this number is 2. So keep in mind how I did that. Every binary number has columns, and those columns have place values, and those place values start at 1 and then it goes 1, 2, 4, 8, 16, 32, and so on, and it keeps doubling each time. So when you have that in mind, it's really easy to see why this number is 6. All we do is we put it into columns. This is the 1's place, this is the 2's place, this is the 4's place, and this is the 8's place. Well, we have nothing in the 8's place, nothing in the 1's place, so all we have left is the 4's place and the 2's place. So we have a 1 in the 4's place and a 1 in the 2's place. So 4 and 2 is 6. That's why this number is 6. You add together the place values that have a 1 in them, and you ignore the place values that have a 0 in them. You can pretend that those don't even exist. Let's do another example. So, I'm going to write out a more complicated example here. Okay, so what about this? All we do is we add together the place values that have a 1 in them. So we have the 1's place, that means we have 1. We have the 2's place. We don't have anything in the 4's place, so we can ignore that. And then we have the 8's place. And then we have the 16's place. And then all you have to do is add this together, and you'll have your answer. So that's how you do it. You just add together the place values that have a 1 in them. Now, this explains how you can convert any binary number from binary, base 2, to decimal, which is base 10. Let's look at how we can add together two binary numbers. So for example, let's say we have this binary number and this binary number. How do we add them together? Well, this is a very easy example because you only have a column that either has all zeros or a 1 and a 0. So here, for example, you have a 1 and a 0. You can just say 1 and 0 is 1 and drop it down. 0 and 0 is 0, drop it down. 1 and 0 is 1, drop it down. 0 and 1 is 1, drop it down. Now, without even converting it to decimal, we already have the right answer, and now we can test it. Okay, what is the top number? We have a 1 in the ones place, nothing in the twos place, and a 1 in the fours place. So 4 and 1 is 5. And in here we just have a 1 in the eights place, so that's 8. And we know that 5 and 8 should be 13. So we can test that. We have 8 plus 4 plus 1, and that's 13. So that's how you do this. Now, what if you have a problem where you're adding together two binary numbers and it's not so simple, where you have, let's say, something like this. You're adding together 6 and, let's say, 7. How do you do this? Well, first of all, you can think of this in terms of just adding together the places that are actually set and then constructing a new addition problem based on that. So we know that 0 and 1 is 1. We know that 2 and 2 is 4. We know that 4 and 4 is 8. And then we have our answer. We just add it together and we have our answer. Now you can do the exact same thing in binary if you want to have the binary answer instead, and we'll do the exact same thing. We'll add together 6 and 7. But this time, rather than writing it out in decimal, we'll write it out in binary. So we have 6 plus 7. Now notice that sometimes I put a 0 in front of the number. That doesn't change its value. You can put as many zeros in front of a number as you want. It's the same thing in decimal. If I write, for example, this, it's still 21. I could put as many zeros before the 21 as I wish. It doesn't change the value. The same is true in binary. So the reason you put a 0 in front is just to make it easier to read. So here we have the same problem, 6 plus 7, but we're going to do it a little differently. We're going to say 0 and 1 is 1. 2 and 2 is 4, but we're going to write 4 in binary, which means a 1 in the fours place. And then 4 and 4 is 8, which we're going to write by putting a 1 in the eights place. We've written out the same problem basically, but now we can just drop down the digits and we have our answer in binary without ever having had to convert it to decimal. So once you are familiar with looking at a binary number as being places that are either turned on or turned off, if there's a 1 in a place value, it's turned on. If there's a 0, then it's turned off. So once you can think of it like that, it's very easy to think in binary. If I want the number 8, I just put a 1 in the eights place, and now I have 8. If I want the number 9, well, it's going to be a 1 in the eights place and a 1 in the ones place, because 8 and 1 makes 9. If I want 12, then I'm going to have a 1 in the 8's place, a 1 in the 4's place, and nothing in the 2's or the 1's place because 8 and 4 make 12. Now, it's very useful to memorize the binary numbers from 0 through 15, and it's very easy to do this. Start by writing 4 zeros. When you write out 4 zeros, that's of course 0, and the next number is of course 1, which is just a 1 in the 1's place, followed by 2, which is a 1 in the 2's place and nothing in the 1's place, and now 3. How do we get 3? Well, we just add 1 to our previous number. 2 and 1 makes 3. We get 4 by putting a 1 in the 4's place. We get 5 by having 4 plus 1. We get 6 by having 4 plus 2. And that's how you do it. Now, notice that there is a pattern developing. If you look at the 1's place, it's always alternating 0, 1, 0, 1, 0, 1, and so on. In the 2's place, it's the exact same thing, except there's 2 zeros and then 2 1s and then 2 zeros and then 2 1s. So the next thing would be a 1 here, following that pattern. And of course, in the 1's place, since it goes 0, 1, 0, the next thing would be a 1 here too. Then in the 4's place, there's 4 zeros, 4 1s, 4 zeros, 4 1s, and so on. So we know the next thing is going to be a 1. And in the 8's place, it's going to be 8 zeros, and then 8 1s, then 8 zeros, and 8 1s, and so on. So we know here that there are 7 zeros, so we need another one. And that is how you can easily take any binary sequence, and by following the pattern, you can count as high as you want. You really don't have to convert each binary number to decimal along the way. Okay, so let's recap here. I know that was a lot of material very quickly, and it actually is not difficult. Binary is very easy. It's simple addition. So if you have a number like this, all you do is you say you have a 1 in the 1's place, plus you have a 1 in the 2's place, that means 2, plus you have a 1 in the 8's place, 8, so we know this is 11. That's all you do. You just add together the place values that have a 1 in them, and you ignore the place values that have a 0 in them. So there you go. I hope that helped you to understand the basics of binary. I highly recommend that you practice yourself, and in order to make that a little easier, I'll give you a simple exercise here that you can pause the video, and then I'll show you what the answer was. Okay, so pause the video, and remember, here are the steps that you're going to do. You're going to first of all figure out which place values have a 1 in them. You don't have to worry about the place values that have a 0 in them, just the place values that have a 1 in them. You're going to remember that the far right place is always the 1s, followed to the left by the 2s, then the 4s, then the 8s, and then the 16s, and then the 32s. So you're going to add together the places that have a 1 in them. So pause the video, and in a few seconds I'll show you how to do it.
So what is that number?
38.
Very good.
Okay, so all you have to remember here is that you have a 1 in the 2's place, you have a 1 in the 4's place, and you have a 1 in the 32 place. So it's just going to be 32 plus 4 plus 2, which is 38. So there you go. That's all there is to binary.
Okay. So it looks like our next material we need to go into is really flip-flops, which is taking some of those gates, putting those together, using some of that logic to build something that's a little bit larger. And I think we're going to need a little bit more time to do that. So here's what I want to do. You have, and let me share this. All right, so inside of, you guys see my screen in the course?
Yeah.
Okay. So in the course, there's a couple different pieces. You've got this practice for number conversions. You can open that up. Like I said, it's basically a couple charts that you'll fill out, everything from decimal, and it gives you different pieces of the chart. Maybe it gives you decimal one time, it gives you the binary number the next time, it gives you the hexadecimal number, and then you have to fill out the chart and complete the chart. And the answers are on the next page. And so you have those answers as well. The other thing is the quizzes. You've got numbering system and you've got binary math that we talked about tonight. 2 quizzes that you can go in, and I know I've said it before, but just to reiterate, those quizzes are not for necessarily grading purposes. Those are for you and your learning purposes. So make sure you go in and take those quizzes. And so I think what we're going to do, looks like we're about about 32 after the hour. I'm going to give you guys this time. I'm going to hang here in case you have any questions or in case you need me. But I'm going to encourage you to use this time to go out, either work on the quizzes, work on the number conversions, just to make sure that you've captured what we talked about tonight. I know that with the constant talk about numbers and back and forth between decimal, octal, binary, and hexadecimal.
This is all in section 8.
Yes, all this is in section 8. Absolutely. Cool. It's session 8. Everything is there. All right. So like I said, I'm going to hang around. So if you run into something, you have any problems, just let me know. If you have any questions, just let me know. But I'm going to let you guys, and if you want to hang in the class and also get into the material, and so you've still connected in Zoom, that's fine. If you want to disconnect from Zoom, that's fine as well. Just know that I'm here. I'm going to hang here until the top of the hour, just in case you have any questions. So just a chance for you to kind of use the rest of this time to work on your own. Any questions before at this point? All right, you guys dive in and let me know if you have any problems. I'm going to turn my camera off, but I'll be right here.
Thanks, Mike.
You guys have a good night. If I don't talk to you, if you decide to log out, we'll see you on Wednesday night.
Thanks, sir.
Thank you.
Absolutely. Y'all have a good one.